heard of MRI?
You mean the ancient kingdom in southwest Nigeria?
No, I'm talking about the revolutionary medical tool that helps doctors diagnose everything from brain tumors to joint injuries.
Oh, you mean magnetic resonance imaging? Yes, it is quite popular in the medical field, but I have heard that many current contrast agents raise potential health and environmental concerns.
Contrast agents?
Exactly. MRI works by causing protons in our body to spin in a magnetic field. When the field is turned off, these protons gradually return to their original state. Since different tissues relax at different rates, we can differentiate between them. Contrast agents are injected to reduce the relaxation time of protons, which enhances the clarity of the scans.
Oh, I see. So the main issue with current contrast agents is their potential toxicity?
Yes, gadolinium contrast agents are the most widely used, but gadolinium can be toxic to humans. There have been cases of gadolinium deposition in various organs, likely due to these contrast agents.
That makes sense. Plus, as we move toward a more eco-friendly lifestyle, we should definitely explore greener methods for producing these contrast agents. So, do you have any ideas?
I had done some synthesizing work on cobalt-2 and copper-2 dityrocarbamate complexes and test their structural and magnetic stability and aim to explore their potential as paramagnetic contrast agents for MRI.
Oh, but why paramagnetic agents?
MRI contrast agents need to enhance image quality by altering relaxation times. Paramagnetic compounds, which have unpaired electrons, are great for this because they respond to magnetic fields.
Was the synthesis complicated?
Not at all. I prepared the ligand by reacting diethanoamine, carbon disulfide, and molten sodium hydroxide.
So it was solvent-free? That makes it a pretty eco-friendly procedure.
Exactly. It is also conducted at room temperature and pressure, which are very mild conditions. Plus, it used almost completely without any byproducts.
For the complexation, did you simply add the metal ions to the ligand?
Basically, yes. However, I calculated the ratio carefully to create a specific complex. Both the ligand and the metal salts were dissolved in their respective solvents. And then, I added the ligand solution dropwise into the salt solution while stirring.
How did you go about characterizing the compounds?
I used several methods to understand the structure and properties of the complexes. First is the FTIR spectroscopy. This helps to identify the functional groups and confirm coordination between the dityrocarbamate ligand and the metals.
Did you characterize the electronic properties?
For that, I used UV visible spectroscopy. It showed the electronic transitions, like the DD transitions in the metal complexes. This helped us infer the geometry of the complexes, whether they were tetrahedral or square planar.
Actually, did you also use NMR?
Yes, proton NMR spectroscopy. It was useful for understanding the hydrogen atoms in the ligand and complexes, though it couldn't be used for copper since its paramagnetic nature causes no signals to appear.
And for magnetic properties?
Exactly. We used a Gaussian balance to measure the magnetic susceptibility of the complexes. It told us how many unpaired electrons were present, which is crucial to confirm their paramagnetic nature. The stability of the complexes was also tracked over time.
Wow, sounds like a lot of work. Are you able to achieve your goal?
Yes, mostly. I successfully synthesized the cobalt-2 and copper-2 complexes with a 1:2 metal-to-ligand ratio. However, the 1:3 ratio complexes didn't form well, likely due to steric hindrance.
And how do these findings contribute to your project?
The results suggest that these complexes could serve as stable paramagnetic agents with potential application in MRI, but there is more work to be done, especially in improving the synthesis and further characterization.
What makes your contrast agent different from existing ones?
Our contrast agent shows exceptional stability, even under UV exposure. This means it won't release free metal ions, providing reliable results every time.
Plus, it is paramagnetic, which enhances MRI images significantly. Hence, patients can expect clearer and more accurate scans. Furthermore, the production of process of this type of contrast agent is relatively simple and time efficient. However, there are some other factors we may need to consider too.
What are they?
One challenge is conducting throughout toxicology tests. We need to ensure that our agent is safe for patient use before moving to clinical trial.
Exactly, safety is our utmost priority. Encapsulation may be required to further improve the solubility of our contrast agent. However, it could increase production costs, which is something we need to consider.
Our goal is to find a cost-effective, greener approach as it uses minimum amount of chemicals during the synthesis process that doesn't compromise the quality of the product.
What do you expect from these contrast agents?
This contrast agent should improve the clarity and details of the image from MRI. Ideally, it should minimize side effects and lower toxicity due to its stability. That's all from us. Thank you.